Hello everyone, let's begin another session in industrial automation. In this session, you will learn the use of high-speed counters in PLCs. So as you already know, the Allen Bradley PLC that we are using uh, has plug-in modules capability. So we can add say, two plug-in modules in these slots. So we are going to use one of the plugin modules, which is the high speed counter, as you can see here. In the Allen Bradley, we have several options of plugin modules available. They can be used for high speed counters, RTD modules, real time clocks, um, thermocouple modules, and so on. So one of the plugin module is the high speed counter, which you're going to learn today. So this is the high speed counter. So it has 8 terminals. So you have to uncover the plastic case, one of the two slots, and you can plug the plug-in module in one of these slots. So then your module is ready. So you don't need to provide any external supply to this plug-in module because the power comes through the back plane and feed to the plug-in module. So as you know, like this is a high-speed counter. So why we need the high-speed counter? Because you already know in the PLCs, we have the normal counters, up counter, down counter, and up down counters. The thing is like when there are several applications where you need high speed, for example, encoder reading. So these encoders, depending on the machine, the speed of the machine, they produce different pulses. So these pulses could range from several hertz to um, several kilohertz range. Normally, you can go up to 250 kilohertz range. So if you use a normal counter for in that application using a digital input, normally we cannot uh, capture all the counts because the PLC scan time, it depends on the PLC scan time. So if the PLC scan time scans the pulses, so there is a high chance when the speed is high, they'll not count in all the counts. So that's the why we need to use external, or some PLCs internally they have the high speed counters. You don't need to purchase this kind of plugin module. They already have the high speed counter digital input, so you can use them. Else, if you use the Micro 20 series, you definitely need to use external plugins module like this. So the purpose of high speed counter and their applications, let's take a look at this video and you will understand more.
High-speed counters are used in industrial automation and control systems to count events or pulses at a faster rate than normal counters. High-speed counters are designed to handle high-frequency input signals and are used in applications where precise counting and timing are essential. A high-speed counter is used to capture the state of the inputs for a PLC or I/O module, and they are used to count the number of pulses received in an assigned high-speed digital input. So what is the difference between a high-speed counter and a normal counter? A normal counter increments by 1 for every clock pulse, whereas a high-speed counter is rapid counting. Speed is usually not a critical factor, whereas high-speed counter features the ability to filter out noise, handle rapid changes, and provide precise counting accuracy at high speeds. A normal counter has a specific max counting frequency. It can usually only handle a few hertz, whereas a high-speed counter can usually handle a max frequency of 100 kilohertz. And so a normal counter is used for conveyor systems, packaging machinery, traffic control systems, whereas a high-speed counter is used for automated robots or CNC machining, high-speed sorting machines, as well as high-speed filling machines. In industrial automation, high-speed counters are used in manufacturing industries to count products at a high speed on the assembly line or monitor machine rotations at a high speed. It is also used for motion control. In robotics or CNC machines, high-speed counters are used to keep track of encoder signals which provide feedback about the position, speed, or direction of a moving part. So, what would require a counter that works at high speeds? High-speed devices or high-accuracy devices. So we know a high-speed counter is integrated into the control system, often within a PLC or dedicated high-speed counter module. That counter is configured to receive and process the pulses generated by the encoder. So as the encoder generates pulses, the high-speed counter counts the pulses to determine the position and speed of the rotating object. The counter can also analyze the order of pulse transitions, rising and falling edges, to determine the direction of movement, forward or reverse. A fast counter is used to count the number of pulses a fast input has received. The high-speed counter is used to capture signal inputs. Normal inputs typically will not have the scan cycle, which is also input frequency, that will allow to count these signals. So, an encoder is therefore used.
Now you have a basic understanding about the high-speed counters and their applications. Let's take a look at the terminologies that is used in encoders. So basically in this session, we're going to use encoders and use with the high-speed counters. So in any encoder, the resolution is a key parameter. So it represents the number of pulses per revolution. So depending on your encoder, so if you need high precise applications, definitely you need to go for high resolution, which has high number of pulses per revolution. The second terminology is the output phase. So normally any encoder has single output. Normally we call it as a phase A. Sometimes they comes as two phase models, phase A and B, or sometimes A, B, and Z. So there are three phases you can use. So what is the purpose of A and B? So normally when the motor rotates, so the phase A leads the phase B in the clockwise direction. If you take a look at in this direction, when the motor rotates clockwise direction, phase A always leads phase B. So in that case, we know like if the phase A rising edge occurs before the phase B, this motor rotates in the clockwise direction. In the anti-clockwise direction or the counterclockwise direction, phase B leads phase A. So even though this is not shown in this diagram, you have to imagine that when in the counterclockwise direction, phase B leads phase A. So you know that the direction has changed. So the purpose of phase Z is when the motor rotates one revolution, this phase Z generates a single pulse. So in that case, you know, this motor has rotated one revolution. So that will help for some sort of like positioning, where you know, like if you know your home position or the starting point, you know, like how far you are from your home position. That kind of applications, the phase Z is useful. The another one is the output duty ratio. You know, like in this kind of encoder pulse, there's a turn on time and turn off period. Sometimes the most often is 50% duty cycle, which means the half of this period is turned on and half of the period is turned off. So if it is not the 50%, sometimes this could change. So in that case, you can calculate if you know this turn on duration and the periodic time. You can divide this turn on period with the periodic time or the T2 time from the T1 time. You will calculate the output duty ratio. Then in any waveform, you know, like the rising and falling edges, that will be helpful when you're selecting your high-speed counters. In fast applications, you need to know like what is how fast your pulses change. The rise time is from 10% to 90% turn on time, and the fall time is when if you zoom out this area, you will see like when the pulse goes down from 90% to 10%, we call this as a falling time. Additionally, all the encoders has outputs. So encoder output is normally connected to your high-speed counter. There are different outputs available: open collector, voltage output, line drive output, and complementary output. So we will learn these things when we come to our high-speed counter datasheet. For now, now you have a clear understanding about the phases, resolution, as well as the direction and the duty cycle and the output types. So once you connect your plugin module to the PLC, so like it is all get the power. Always it is better to turn off the power of the PLC before you do any removal or insertion of this kind of plugin modules. Otherwise, it could damage your PLC as well as the HSC module. So make sure you turn off the power and then connect your plugin module to the one of the slots. So as you can see here, this plugin module, HSC plugin module, has 8 terminals. So they are labeled from 1 to this side is A and this side is B. So pin A1, this one, is output minus and B1 is output plus. So why we need output? Sometimes we can connect coils, pilot lamps, or encoders. Sometimes external power. In that case, we can drive some loads using external power supply, and we can enable this output to whenever from our code whenever we need to turn on a pilot lamp or coil, or sometimes the encoder itself. So it can be wired in syncing output configuration or sourcing output configuration. This voltage can vary from 5 volt up to several volts depending on the datasheet specifications. So this is the single output that is available in this plugin module. And now these are our 3 inputs or the 3 phases. If you take this A minus and A plus, which are for pin number 2 and pin number 2 in A and pin number 2 in B. So we can connect one phase from the encoder to this one, and the phase B to these channels, and phase C to these 3 channels. So then your encoder wiring is completed. The output is optional. Sometimes you can you keep this floating, because if you don't use any output driving, you can only wire your phase A, B, and C. Now, there are different types of encoders available in the market. For example, now in Allen Bradley also, they have 845H series encoder. It is output is differential type. So if you use a differential type encoder, so this is the how you have to do the wiring. So A of the differential output has to be connected through to A plus, and A bar should be connected to the A minus. Likewise, the phase A, B, and C can be connected to your HSC module. So it has internally the resistors as well as this optical isolator. Depending on the signal you receive, it will generate some logic signals, and that will be used for counting, and the count value will be forward or the communicated to your CPU. So sometimes you need to use an external power supply to power your encoder. In that case, you need to use long wires, the power wire as well as the signal wires. So shielded cable must be used. So shielded cable should be earthed in one point of the system. It should not be connected in both sides of the system, either from encoder side or your HSC module side. You have to connect it to the protective earth for noise immunity. The other one is single-ended encoders. Here also you can use it single-ended, which in that case the output type is there's a transistor. There's a common terminal in each outputs which are connected to the ground. All the emitter of the transistors are connected to the ground, and all the collectors are pulled up to the VS using these resistors. So in that case, if the encoder is, let's say like it is incremented, if there's a logic 1 comes, which means this is turned off, there will be this, if this transistor is turned off, you can see here the voltage at point A will be high because this line is pulled up. So that signal goes to A plus, and when the transistor is turned on, then this A will be pulled down to the ground. This voltage here will be 0. So likewise, depending on the pulses, the voltage will be high and low, and that will be available in your HSC module. So this is one way of the outputs in encoder. There are some discrete device wirings as well. Here you can see 3 types of encoders outputs are available. Here the emitter is connected to directly to the A plus, and the common of the encoder connected to the A minus. When the encoder signal is high, that means the VS is, when the transistor is true, VS will be passed to A plus. This will come true. When the encoder signal low level, output will be 0, which means the COM is 0, this is 0, the encoder receives a 0 volt. Likewise, there will be ones and zeros of high frequency pulses comes to this encoder. And here, this is a open collector type configuration, and now that is sinking output. So here the VS is connected to the VDC, and the output is pulled up with the resistor, and the common is connected to the common or the ground. So when the logic high, at logic high, this will transistor is turn, let's say, turn on, which means when the transistor is turned on, this becomes shorted to the ground. This voltage will be 0. When the encoder is 0 point, which means this transistor off, this voltage here will become high. This is another configuration like a op amp. You have VS supply in, output, and COM. So the output is high when it is true. Then it will drive the encoder with logic high. When this is 0, the output voltage becomes 0, and this voltage becomes 0, and the encoder signal is 0. So there are different types of encoder outputs. You have to refer to the manufacturer's specification of the encoder itself, and then you have to do the wiring of your highest speed counter module. Then let's take a look at the input-output specifications. Input, you can use one quadrature differential input for phase A, B, and Z. Input voltage, your signal voltage level could range from 0 to 30 volt. That is your encoder pulse voltage. For example, this input A, it can change from 0 to 30 volt. On state voltage means this encoder can detect from 2.6 to 30 volt as a logic 1. And the on state minimum current is you have to at least provide 2 milliampere current to this encoder channel to turn on this one, because there are some optical like optocouplers, and the LEDs has to be turned on with at least 2 milliampere current driving here. So these, if you use this kind of pull-up resistors, you have to be careful the value of these resistors to satisfy the minimum current to turn on the channel. On off state voltage max is 1 volt, which means like you have to keep this low voltage level lower than 1 in order to detect it as a logic 0. There are some leakage currents like 1.5 milliampere, and input current range, even though it is the minimum is 2 milliampere, it could range from 2 to 9 milliampere. You can go up to 9 milliampere current to this channel without distorting the device. And the input impedance is normally 3580 ohm. So if you take a look at from this end, the total impedance including these resistors and the nonlinear devices like these photovoltaic diodes. Total impedance of this channel is 3,580. So the pulse width minimum turn on time has to be 200 microsecond. Phase separation, this when you have phase A and B, at least you have to keep 2 microsecond delay. Normally, these phase A and B are separated with 90 degrees phase shift. And you can drive up to 250 kilohertz with 50% duty. So this high-speed counter can measure the rotating speed up to 250 kilohertz or the number of pulses up to 250 kilohertz. Then we have the output. So you can see here, there's only single output available in this device, that is O plus and O minus. That has to be wired with the external power source, either from sinking output or sourcing output configurations. So you can use up to 5 to 30 volt power supply to power it. And now, even though it is mentioned 16 outputs, one is the physical output and there are 15 virtual outputs. Those are just memory bits when you call in this output to enable. So this is, you can just think about like it's a one single physical output that you can turn on and off. So this channel, the output channel, can drive 0.5 ampere current, which means even though you connect 24 volt or 5 volt supply, the maximum current that it can go through this channel is up to 0.5 ampere or 500 milliampere. Output on state current minimum is 1 milliampere. Which means like you can drive very large impedance load. So you have to keep at least 1 milliampere current driving through the channel, otherwise it won't work. For pilot lamps, it is okay. For example, let's say like you use a high value resistor like 100K or any large value. Now we're providing 5 volt supply, and this load resistance should be enough to drive at least 1 milliampere current through this channel. Otherwise, the channel will not turn on. And on-state voltage drop, like any this output has driven from MOSFET or transistors. They have a voltage drop across these devices that is typically 0.5 volt. And there are some leakage currents due to the circuit parasitics, and that is low as 0.5 milliampere. And you have turn on time maximum 2 milliseconds, which means even though you energize the channel, it takes 2 milliseconds to turn on or to respond to your signal. And if you turn off the channel using your command, it takes 2 millisecond turn off delay to really turn off that channel. Reverse protection polarity is not there, which means if you mistakenly provide plus and minus, sometimes that could damage your device. So you have to be careful. This side is always positive and this side is always negative. Otherwise, that could damage your device. Another important thing is the derating. Derating is even though you rate your device to certain level at the normal operation, depending on the temperature deviations, the working conditions might change. For example, now maximum input voltage, which means if you have this kind of encoder signals comes to your high-speed module, 30. So that voltage you can keep only in this range, -20 to 30. So if your temperature of the ambient temperature, the environmental temperature changes, goes more than 30. So this voltage has to be reduced to following this curve. Normally, if your ambient temperature is at 60 degrees, you cannot operate the encoder signals with 30 volts. So encoder signal should be lower than at least this value, around like 26. Normally, if you operate with 24 volt encoder voltage, you can go up to, I think, 70 degrees, minus 20 to 70 degrees, if your encoder voltage is 24 volt. So if you're operating at 24 volt, you know, like your operating is within the limit without having any derating. And the output voltage, when you connecting these output devices, you can connect from the voltage level could be vary from 5 volt to 30 volt, and it also has a derating. If you drive it with the 24 volt DC supply, when the ambient temperature goes from 30 to 70, the voltage that you can feed from your external source has to be reduced to these values following the curve. For example, at 65 degrees, it should be low as 26.4 to safe run. But if you run at just 5 volt operation, if this voltage is 5 volt, then there's the derating is minimum. You can see here 5 volt operation, output current is can be kept as 0.5. That is the output current, but if you use 24 volt DC operation, your output current capability will reduce from 0.5 to low value with the increase of the temperature. So that is all about the technical specifications of this high-speed counter. When it comes to programming of your high-speed counter module, you have to use this reference technical manual, which is 2080 MOT HSC, which can be downloaded from Rockwell Automation website. Here, there are some definitions. This is our high-speed counter module. You can see these are the outputs. You can see here this A, B, Z, and 0. This is the output. When you're providing pulses to this module, there are some small LED indicators. You can actually see like A is blinking. So they can be used for just visualization, whether you are receiving a signal to this high-speed counter and it is working properly. And there are several applications of this high-speed counter, as mentioned in this application examples. You can use it for linear encoders that can be directly coupled here, or sometimes in the servo drives, it is driving a servo motor, so that it is feedback driven. Sometimes there could be a feedback output that can also be sent to your PLC just for reference. And there are several user-defined function blocks available for this high-speed counter plugin module. But in this demonstration, we just learned the array_hscp plugin module. It looks like this. There are a certain level of inputs and outputs. Now you can see function block FB enable, which enables this function block, and slot ID is the number, plugin slot number, whether it is 1, 2, 3, and 4. Because you know, like Allen Bradley, we have the slot 1 and 2. You have to use the correct slot number depending on the plugin module that you use. Whether if you plug in here, you have to set it 1. If you plug in here, you have to set it 2. And here you have the noise filter. Noise filter is if you use 0, 0 in that define 0, 0 here for this noise filter, there won't be any filter. If you have a lot of noise in your signal, you can use some sort of filtering that will filter out any high frequency noise. And there are several modes available, 0, 2, and 4. I will explain them later. And start is if you set this true, it will start counting, and if you set this stop, that will stop counting the number of pulses. If the enable output is an output, these are the outputs. So if your function block is initialized and if it is enabled, you can get this as an output in your PLC program to verify that it is actually enabled. Otherwise, there's a configuration faults or anything that like your function block is not work properly. ID check is whether HSC plugin module is in at the selected slot. If there's a damage or anything, you will see any ID check as false because they are wrong plugin or not plugged into the correct slot. It is just an indication whether the plugin module is in the correct slot. Initialize indicates true if the HSC initialization is done correctly. Accumulator gives you the number of pulses received from the starting point where you enable your start. And the rate will determine the rate of pulses per second. That is direct measurement of the speed or the frequency. Here you can see a running example in connected component workbench when you design a ladder diagram. This is the HSC plugin module function block. So if you enable the function block, this will become true and the output will be set true. And slot ID represent the slot where your plugin module has connected. Here it is slot number 1, and there's no filtering is used. That is why you have 0, 0. And mode is selected as 6. And begin count becomes true, which means now the HSC module is counting the number of pulses received. And the false stop is false, which means you are just counting and you have not stopped it. ID check is true, which means the plugin module is correctly at the correct slot. Initialization is true, and accumulator displayed 2209 pulses received, and the rate is shows 0. So there may be actually it is not running there won't be any accumulation over the time. That is why this is not updated. If it is actually running, this accumulator should be updated as well as the rate should be displayed. Now take a look what are the counting modes available in this high-speed counter. If you use the mode 0, here you have to define the mode. What is the mode that was required? If you define mode 0, which means it just acts as a up counter. If you use mode 2, the counter with external direction, whether you are rotating it as clockwise or anti-clockwise direction. If you use mode 4, it is the 2 input counter, which means up and down. You can count up or count down. Normally we use mode 6, which means it acts as a quadrature counter and phase in inputs A and B. You won't use that as a quadrature X4 counter, which means it is 4 times, the resolution is 4 times more than normal quadrature counter. You have to use mode 8. If you want to double the resolution of a normal quadrature counter, you have to use X2 mode. And if you use mode 12, it will just act as a down counter compared to the 0 counter. So the quadrature counters, you can refer them, what's the purpose of them. Normally, we have the normal counter, quadrature counter, and if you want to increase the up to 4 times the resolution, then you can go for quadrature X4 counter. For example, now you have phase A and B. If you have phase A and B like this, if you use a normal quadrature counter, this will only count the phase A pulses. And if you use X4 counter, which means you can see there are some 4 logic states. This is true and this is false, and this is true and this is true, and likewise. You will get 4 counts within a single pulse, which has a high resolution compared to the single counting. So then we can see how this can be programmed in the connected component workbench. Now we are in the connected component workbench. So this is a example program. Here this array HSC plugin module function block is already imported to this ladder diagram. All you need to do is defining these inputs and the rate and the accumulation, the initialization and ID checks. These outputs will be updated when you run your system. So just go to the local variables. Here, these are the local variables assigned for with the function block. You have to select the slot. Here, slot number 1 is used, which means the HSC module is plugged to the slot number 1 in the available slot in the PLC. Mode is selected as 6, which means it acts as a code pressure counter. And the noise filter is set to 0, which means you are not using any filtering. So those are the only initializations. You don't need to define any global variables. Once you have clearly defined these inputs, and you for start and stops, you can define it. If you set the start true, then it will count. And if you set the stop true, then you can stop the counting. Normally we set the start to true. Here you can see start is set to true and stop is set to false. Those are the things that you have to configure in your connected component workbench. So then you can build your program and download it and test it.